Yeah. So today we'll be discussing about the SVM classification with respect to non-linearly separable data. Okay, the main important point about the linearly separable data, we have seen an example of it. We have two Cartesian coordinates, it's a two-dimensional, and you have the data which is scattered. We draw a hyperplane for that, that's the regression line, and we find out the margins for it, and we get to know, okay, based on wherever the positive or the negative points come with respect to the slope of the line. If it is above, the data points are above the line, all are positive. The data points below the line, all are negative. And the final classification that we do using yi into w transpose of x should be always be greater than 1. The value of it should always be positive. If the value of it is positive, which means that it is a correct classification done. If the value of that is negative, the multiplication term of that is negative, which means it is not a correct classification. There's false classification happening. Okay, so this is what we saw it, and we also saw if what happens when the errors they fall within the margin and how do we go ahead with that. We saw the regularization problem also, like how do we solve that. Okay, now we go ahead with the non-linear model. When I tell non-linear model, this is actually the statement of the non-linear model. Okay, but I'll tell you what it is. Okay, let's go ahead with the example and I'll then come back to the definition for our easy understanding. This is one of the example that we have. See, most of the terms normally state that whenever you have a data which is non-linearly separable in a two-dimensional space, we transform it into a higher dimension, like from the lower dimension to the higher dimension. Basically, when we tell that the lower dimensional values are nothing but the two-dimensional which we get, okay, when you get something like this, okay, I have x1 and x2, I have all these red points and I have all these blue points. So when I just try to draw a linear line, a regression line like this or somewhere like this, how do you feel? Do you feel that the data can be classified correctly when I have such a problem like this? Do you feel that the data can be classified correctly?
No, ma'am.
Because either of these points lie on either side. It can fall on, because you have these points. I will tell, okay, I have a red point here, again I have a red point here. Okay, so neither the classification problem is correct over here. Like we will not tend to go to a correct strategy, because and most of the time we get it lesser than 50% of it, because most of the points lie on either sides of these categories when you're separating it. Okay, so what we do is we transform that. An attribute transformation is happening. Okay, it's basically what I write is this type of data that I have. Okay, when I draw it in a linear line, just one single dimensional, to show you how it is, because I will get it like this. The same plot, when I look at from the top down approach, it might look like this. Okay, and now what I do, I have to transform it. As I've already told, linearly separable data, non-linearly separable data can be classified or can be applied with SVM when they are transformed into a higher dimension. How we do that? Now I'm just writing this non-linearly separable data as phi equal to x. Okay, I am transforming that. A transformation is applied onto it where I get the final transformed as phi of x. This is phi equal to x, but here I'm transforming it into phi of x. How do I transform that? Okay, so these are quite visualizations you have to go ahead with. Okay, now how I'm telling here is when you change the data, okay, the interpretation of the data, the value of the data remains the same, but the way it is interpreted, okay, the value of it remains the same, but the way you interpret that from one dimension to the other dimension, all the time it makes the data points to be separable like this. Okay, imagine yourself in a three-dimensional now. Okay, I have a three-dimensional data. Yeah, I have a three-dimensional data. Now in the three-dimensional data, when I'm plotting like this, okay, I have a three-dimensional data like this, and I have it. Okay, I have points one here and one here. So what I do over here when I'm transforming, because this was in completely non-separable data. When I plotted in a two-dimensional, it was all clumsy everywhere. All the points were lying. Okay. Now what I do is I'm transforming that into a higher dimension. When I go to the higher dimension, suppose let me take the three-dimensional. Okay. So the three-dimensional space, you know, right? It will look, you have to visualize, you have two red and the blue points. Now what will happen when I'm transforming it, the data points will lie like this, all the red points to one side, maybe all the blue points to the other side. I mean, the other orientation. There's a picture of orientation here because the data which I looked in the two-dimensional was just like at a Cartesian coordinate that we observe it. But when I see it in the three-dimensional, okay, now I have all these points here. From one plane, when I look, it is over here. From the other angle I look, it will be over here. So I have two things. If you're able to observe, I have two different things. And in between them, I will be drawing a hyperplane in such a way that I will consider this as my hyperplane in a three dimension. This is a sheet of paper, okay? This is gonna be a hyperplane with respect to three-dimensional. So since my data is on three coordinate systems, okay? So I have it towards x-axis. You consider all the blue points are towards the x-axis, okay? All the red points are towards the y-axis, to the x-axis, and y-axis is this way, okay? So over here, when you have these data, we will be drawing a line like this. Okay, you can imagine a line which is drawn like this, example, okay? And which is drawn like this. So what happens? All my blue data is over here, all my red data is on the above, but it's in the three-dimensional now. Okay, so when I look it from the three-dimensional, okay, for your easy understanding, okay, let me just keep it like this. Okay, so now what happens? All my blue points is here. This is my z-axis right now. So all the blue points are here, all the red points are here. So I can create a separable data there in three dimensions. Example, okay. This is just for your understanding. I don't know. I'm just trying to put it out like this. When I was trying to visualize this, okay, because I was not able to get, okay, how this transformation is happening, how the data value is going to change. Okay. So when I asked a question to one of my professor, he told me something telling that, okay, so when you get ready yourself, suppose the day when he was explaining to me, he told me, I was in a class with very formal, I mean, a normal student who was in the class, okay. And then he told me, okay, you get ready a day and come. Okay. So what he did was, we were all in a class. They took a picture of us. And after that, again, after a few days, there was an event that happened and we all were ready to the college and we went there. And when we asked again, see, he told us to get ready and come, and today we are here. Okay. He told, okay, let's have a group photo. We took a group photo. There was so much of differences between the previous photo to this photo. And he was telling, what is the difference? We just laughed and we told, sir, it could be something like that day we were not dressed up well. Maybe today we are dressed up well. So that's the reason there's a huge difference in the photo. Okay, which means that you are the person. You are a data point which remains the same. Whereas when you give an orientation to that, orientation in the sense, okay, your presence, again, I'm telling, it's your presence. When your presence, that orientation is put on to you, obviously you look much good, right? So it means that for a data point in its orientation, in the two-dimensional orientation, when we look, it's the same data point, but it's so clumsy. You cannot identify what is what. But as you go on for the higher dimensions, the three-dimensional, see, a fourth-dimensional visualization is very difficult. But whereas at least a three-dimensional visualization, we will be able to imagine that from our side. So whenever you change the orientation, because there's an angular picture that comes into for that particular data point. Okay. So when that angular picture, all these are values. Okay. These are just values. Orientations are nothing but the angular values. It's just a value given to it. Okay. But when that value is added on to that data point, the interpretation of that itself will change. It goes into a different dimension. When it goes into a different dimension from one plane to the other plane, when it changes, obviously you will get a gap between that where you can construct your hyperplane. That is what the basic logic of transformation means. You're changing its position. Obviously, I don't know if you have read through computer graphics, in that you'll have the transcaling, reflection, or you have translation. You have all these things, right? What do? It's the same data point they take up, but they change its orientation. They change its placement in a different dimension. When you do that, you get so many good results out of it. That's why data augmentations. You remember the term data augmentation? What does augmentation mean? You have the same data, but you rescale it into a different values. Rescaling, what do? A concise or an enlarge of it. It's within the same dimension itself. You just scale it to another dimension. Data point remains the same. Once again, when you rescale it back, you'll get the same data. So this is how you can manipulate your data and come to a solution. And this is how a lot of research is still involved in these activities, where from one dimension to the other dimension, when you scale, you can play around with those values. Okay, so this is what transformation mean, and it is quite too complicated. Okay, too complicated in the sense computational cost. Okay, the computational cost is actually high comparatively. So even though the complications like the computational time is high, but still you are solving a huge problem which is not possible in a two-dimensional data. When you move it to the higher dimensions, you are able to solve those problems. Such transformations, we call it to be as a kernel trick. Okay, SVM kernel trick. It's nothing but when I told this, okay, they're changing its orientation. There is a value that is added onto it. What is that value? It's a constant. Kernel itself is a constant here. Okay, but you're trying to change, you're applying that constant to all the points and making its orientation different. Okay, so kernel trick, basically what we call it to be as the SVM kernel or the SVM kernel trick. It's nothing but it's a dot product. Dot product itself is a constant. You're multiplying it with a constant. It's a dot product of the features, okay, that are similar. The dot product of the features that are similar. So when you visualize it from one dimension, when I change it to the other dimension, it means that I'm adding some constant, I'm multiplying it with. So there's a dot product of it that is applied onto the two-dimensional data to make it into a three-dimensional data. Okay, so when you do that, obviously, as I told you, see, you can see here, you can just imagine there, I have a data. This is the three-dimensional data. I'm just gonna place a hyperplane. Hyperplane is basically when in three-dimensional, when I look at it, it will look like this. It's a page of a paper. It's a plane. It will be a plane. In a two-dimensional, it is just a line. It's a regression line. When it goes to three-dimensional, it is going to be a plane like this, hyperplane. Okay, you just cut it like this. In two-dimensional, you can see it looks just like a line for you, right? But whereas in three-dimensional, it looks like a plane for you. Okay, so this is what we are trying to come up with. So the diagrammatic, whatever I've written over here is like this. Okay, now I can easily draw a line in between that and make it separable. Okay, so feature space after transformation is almost linearly separable. Okay, and let's go ahead with our definition. I'll just clear this. I'll go with the definition. What does that mean? Okay, so it's basically, it is telling you I have a function g of x is equal to, okay, g of x is equal to w transpose pi of x plus b. What was this line? Y is equal to mx plus b, or y is equal to w to the power of x plus b, right? Y is equal to w transpose x plus b. This was our linear regression line. For that, we used SVM, applying the margins, we calculated it. You can see now, the same way I'm writing it as g of x. Y transpose is the same. The value of x that I got it in the two-dimensional over here, the below part over here, I'm transforming that into phi of x from the lower dimensional into a higher dimensional value, which is phi of x plus b. This is the expansion of it. Okay, there's the constant alpha that we are applying to it into phi of x1, transpose of it, phi of x plus b. It's a similar representation of it, quite different. Okay, a kernel function here is defined as a function that corresponds to the dot product of two feature vectors. And one more thing, why do we term it as vectors is, as I've already told you, there is something where we call, when we give an image to a learning system or to an SVM classifier, it will convert each and every data point into a vector. Each and every pixel is converted into a vector format, and only then it processes. You cannot directly give the raw data to the system. Everything is going to be converted into a vector format and then going ahead to process. Okay, so a similar here also. If suppose I remember we discussed a lab program also, right, with respect to, there we had a count dot vectorizer, right? So it converts each and everything in the form of a vector, even the text, the pixel, the data point that you give, any type of it, it converts into vector and then processes it. Okay, so it corresponds to a dot product of the feature vectors in some expanded feature space. I have an expanded feature space and it's going to be the dot product of between two feature vectors, and I get the transformed three-dimensional data where I can have a linearly separable plane that comes between the data that I have. Okay, this is very, very important because you will be using this kernel trick in most of the real world examples. Over the few decades before the deep learning concepts, it was all about SVM, support vector missions. You can see huge papers being published with SVM, so many applications being solved using SVM classifiers. And beyond the SVM, now we have the convolutional neural networks or any other deep learning networks that has come up as an extension taken from the background of SVMs. Okay, so as I told you, it's just a constant multiplication for the visualization purpose, but it's a dot product of two feature vectors when we perform it as per the theoretical concept. Okay, so how do we do that? Okay, there's just a small derivation for that. Okay, it's telling the kernel example. I have a two-dimensional space x1 and x2. You can imagine yourself that you have a two-dimensional space of x1 and x2 with this. And the points, I will write it as xi is equal to xi1, xi2. For xj, it is going to be xj1 and xj2. Okay. Now, when I'm substituting, there's a formula for the kernel function. As I already told, it's going to be the dot product of two things. So I have to come up with that. So I'm going to write it as kxi comma xj is equal to 1 plus, if this is with respect to your statistical problem statements, okay, from mathematics which has been derived, it is 1 plus xi xj the whole square. It's similar like a plus b whole square. Okay, but you have to note over here, xi value of this, xj value of this, when you substitute over here, and it's again going to be a dot product here, okay, the whole square with 1. When I split up that, when I apply it, and when I split up the whole square of it, okay, I will be getting an equation like this. Okay, to prove with respect to the kernel trick, okay, they came up with this dot product, which is called as, they split up these two terms into two different things, okay, with the dot product of it. And finally, they arrived with a solution like this. I just wrote this for your reference, maybe in case you might require how did we get out to that dot product. Okay, this is a derivation from the Merce's theorem. Okay, you can have a look at it whenever you have some time to go ahead with these things. Okay, so it's been derived from the Merce's theorem. Where the dot product of two feature vectors that are to be similar. Okay, so this is about your kernel trick. Okay, and there's one more thing, important point that I told. The most commonly used kernel trick, when I have to tell about the kernel tricks, okay, I hope you'd have been read about RBF, the radial bias function. It is one of the most widely used kernel functions with respect to SVMs. So how is that? It's nothing but it's the Gaussian noise. Remember, we had the bell curve Gaussian. From where did we arrive these data points? Okay, so the Gaussian data points, so it is applied through that. Okay, so it's a radial bias function. Let me go one ahead, one after the other. So this is going to be the senior linear kernel, okay, which is nothing but k of xi xj is equal to xi into xj. We perform this, it's just a dot product of this that we perform, that's fine. When suppose I wanted to go ahead with a number of powers, okay, a two-dimensional, three-dimensional, a polynomial powered, okay? What I do over here, the same equation, the previously we applied it, right? 1 plus xi into xj. The whole square is for the two-dimensional. For the three-dimensional, I can go with 3. For n-dimensional, I can change this power. Okay, so this is going to be the polynomial of the power. The same, I have the same equation written out for this derivation. You can see 1 plus xi into xj the whole square, where xi value I changed it to xi1 comma xi2, where xj value was xj1 and xj2. I derived those equations writing it with the form of square roots. So finally the dot product of it, which came down to here. Okay, so this derivation is completely mathematical. Okay, along with that, so now when I use it for the two-dimensional, I'll write it as 2. When I go for 3 and the higher degree polynomial, I will be writing it so. This is very important, the Gaussian, which is the radial the basis function. Okay, so this RBF, we write it towards, if you remember the Gaussian curve, the bell curve, and we were discussing, we wrote an equation. Okay, e to the power of 1 divided by square root of 1 plus e to the power of something into e to the power of minus, we had xi minus mu the whole square divided by sigma square. Okay, xi minus mu, it's similar here, e to the power of minus of the modulus of xi minus of xj the whole square divided by 2 square root 2 sigma square. So the same Gaussian, this e to the power of term, whatever we had, I'm just considering it for my constant value here. Okay, with respect to mu and standard deviation, the mu is converted with respect to xi minus of xj the whole square, and your standard deviation remains the same derivation from your bell curve. Okay, so this is about your Gaussian model. This is the most widely used kernel tricks, and this is how, even when you call your SVM function, and most of the SVM functions, the default is going to be the radial basis function, and you can just check out, okay, what internally happens is they actually apply this kernel trick on the transformation functions. Okay, and this is about, the last one is about the sigmoid. Okay, sigmoid, where they use tan h, beta 0 into xi. It's going to be xi over here, xi into xj, beta 0 and beta 1, they are the constants. They are the coefficients which has been applied for the sigmoid curve. Okay, so in general, there was one more which I thought to tell you. So the functions that is satisfying the Merce's condition, as I told you, it has been derived from the Merce's theorem. Sorry. So they can be the kernel functions. From the Merce's theorem is what we came up with this kernel function. Okay. Example that I've quoted over here is, these are non-linear separable data. Okay. So when I go ahead with these non-linear separable data, what happens here is, let me consider solving this in the linear way. Okay, these are the 3 different kinds of data that I have. Okay, it's all scattered. It is all scattered and it is all present always. Now I wanted to separate this. Okay, first what I try is I draw a separable line like this. I create its margins. I go ahead and check, okay, what is the distances between these margins and how does that happen? I'm just checking it out. One possible way. The second possible way is I can just divide it like this. And I again create the margins. Suppose, let me consider, I'll create margins from here to here. Do you think this will work? Something like this, when you have all the data which is clumsy and it's given to you, do you think that this can work out? And I will say this is in 2 dimension. I'm trying to extract your understanding now. I want the class to be interactive. I have something like this, the data. Okay, let me again clear it. I have, this is my data right now. How do I go ahead with separating? How do I classify it into 2 different classes for red and blue? How do I do it? Do you think by just drawing a line in between like this? This is all a 2-dimensional data that I have. Do you think it will work with linearly separable? Like a linear regression, I draw a line like this, or I'll draw a line like this, or I'll draw a line like this. So I have 3 different lines that I've created and its corresponding hyperplanes. Sorry, the corresponding margins. Do you think it will work out like this? Answer me, do you think that would work? When you just create a linear regression line for this type of data, will it work? When it is non-linearly separable? Can I use the linear regression lines or the normal SVM with linear lines? Does this work?
Because however you try to draw the... Ma'am, are these the two reds different colors? Or are they same thing?
Okay, let me consider this is the light red. This is a dark red. Now you have three different colors. Now you tell me.
Then linear.
Then linear, we can go ahead with linear. How can we do it with linear?
I mean, like, we need two lines. We can't.
And this is where you use kernel regression, ma'am.
Yes. At least thank you. So I made you understand the concept. Okay. So when I'm trying to do with this, okay, wherever I try to draw a line, okay, with respect to this, a linear line, when I have three data points like this as well, but it's actually difficult for me to go ahead with something like this. Or even if you consider both are red, just red colors, and there are only two different categories of this. For me, drawing a line anywhere, the hyperplane, when I try to do any kind of it, I will not get my accuracy correctly. Classification accuracy will always be between 50 or 60%. It cannot improve more than this. So to solve such kind of problems, we can go ahead by using this kernel trick, okay? Can be solved by using the Gaussian kernels. How do I do it? Imagine this is right now in a three-dimensional space, okay? Let me clear this. That's one of the reason why I drew this, okay? So now the similar imagination that I wanted to have is, this is my two-dimensional view for you, and the third dimensional is from your end. You have the three-dimensional view. So from my end, I'm looking at it as a 3D, okay? What happens over here is I was able to observe that few of the data points were lying over here in the third view from your side, okay? You have your third view. So few of the data points was lying here, okay? Few of the data points lying here, few of the data points lying here. When you transform those things, obviously there will be a differences that will be observed, right? So at that point of time, I can draw a hyperplane between them. I can create one hyperplane here or one hyperplane here on above because they were all the data points above, and one hyperplane like this to categorize it. There are cases of multi-class classification also which performs the same way. If you have binary classification, you have multi-class classification. It performs by separating. Your main intention is you have to separate it. But when I tell, okay, I have this data with respect to, this is just a red color. I have only two. I'm right now concentrating only a binary classification problem, okay? If I go ahead with the binary classification, it's only two colors, okay? So with those two colors, I have to perform the classification. It is not possible. But here, with respect to this, I've put up something. It is two lines, okay? But for you, you can just imagine, I've just written a separation. I'm sorry. I've written a separation like this, but when you visualize in the three-dimensional, with one single plane, I can classify all these three. So you can just consider this as my blue points. I should have given a color differentiation. I'll do that. Okay, this is the red point and this is the red point. Okay, so all the blue points, all the red points. So what happens over here is, by imagining, as I told, all the blue points are lying below. If you consider, all the red points will be above that. One simple hyperplane, when I draw it in between these two, all the blue points and the red points will be segregated easily. This is just a visualization for you. I don't know why this is coming. Okay, the visualization for you. Okay, when I put it into a three-dimensional, the two colors itself will fall under different dimensions. Though it is scattered over here in this picture. Imagine this was the same picture where I had it in the circular format in the above. When I had the circular format in the above, what did we do there? If you can observe it. See here. It is in the circular format itself, but here I just had one color here, the center color here, and it was divided like this. Just one plane to divide it. But when you look at the top view of it, okay, the top view of it or the way it has been scattered, so you'll have two different points like this, two clusters of red color itself, and the blue color will be the bottom. You can directly draw a line in between them, but they have, you can actually visualize those three different points like that. But if it was a graphical representation, it was nice, but it's basically like that. You have two different clusters of red and the blue clusters, but you can separate it with one single plane. Okay, so this is, I wrote it for your understanding how it will look like. Okay, the session will get closed in 1 minute. So probably I want you to think about, we'll go ahead with the artificial neural networks concept. We'll start with this. So till now, whatever we discussed was with respect to the SVM, the linear separable data and the non-linear separable data. The linear separable data can directly go with the hyperplane, okay, because it has a direct classification with respect to two-dimensional. Whereas the non-linear separable data, we have to convert that into a higher dimension and then go ahead with the kernel trick. And we have already seen what the kernel trick is about. So all this ends your SVM classification. If you have any queries, if you have any doubts, you can let me know. After the session ends, we'll again reconnect back and we'll check out what is about your artificial neural networks. Any doubts with SVM? Please go ahead. No doubts? All clear?